right, so continuing on with the lesson, now our topic is going to be go to radian measure, and I understand now that it's not something that in the change of the curriculum, now we're going with integrated math. I don't think that you get as much trig as they used to in the old days, and students would have maybe a better grasp on radian measure. So we'll go with the assumption that we do not know radian measure. You know, what is it? So still a different way to measure an angle. We'll talk about, you know, what is the definition. So I've drawn an angle here, but I've drawn it in a circle, and I've tried to draw it in standard position. So if you can picture the XY plane, you got the XY plane there, but I did a circle so that therefore the rays of the angle here, if you just go from the center of the circle to here, is also the radius of that circle, okay? So the way radian measure works, if you can answer this question, then you'll have the radian measure. It's the number of radii that fit along the intercepted arc of the angle. So the way I like to describe this is, think of your radius as those pipe cleaners. When in elementary school, you would make maybe different, maybe even, I think we made ornaments one year with pipe cleaners when I was in elementary school. So they're flexible. Take this radius and see how many of this length here would you think would fit along the arc. Whatever that is, then that's the measure in radians. Now, someone would think, well, how can I get a straight line to fit along the circle? Give me just a second. Here's how a straight line fits along the circle. You got your tape, all right? Rolled up there. And look, a straight line can fit along the circle, all right? So I'm just going to guesstimate. So I can see that the radius is about this long, but I'm imagining it to bend. So if I were to take this segment and bend it, I would say it might go to about here. So that looks like one radii, another radii. So I'm going to guesstimate, and it's still, if I draw like this to show that it was constructed counterclockwise, I'm going to guess that this angle is 2. And you don't put any units, you just put a 2. Now you can write the word radians so that you understand that it's radians, but you don't have to put that. By not putting a degree symbol, then we know that the angle is radians, because that's the only other angle measured. And it's the number of something. So we don't put, it's just telling you how many radii we think would fit along this. So I'm saying that this right here is one radius, and this right here is one radius. Okay, that length. Now, it would be much easier if I knew these lengths. Okay, so the length along a curve, that length there, that's called the arc length. And we typically denote this with the S. Okay, S is used for arc length. You don't use A, because A is already used for area. And of course, there's the radius. So if I knew this length and the length of the radius, then I could do it. So let's say I knew that the length of the arc was, say, 24 units, whatever those are. Let's say it was 24 centimeters. Let's say that the radius is 12 centimeters. All right. So if I know how long this is, and I know that the radius is 12 centimeters, then it makes it easy. I can simply do division. If I want to know the angle, I can just take my arc length and divide it by the radius. And that should tell me how many radii fit along the arc. So 24 centimeters divided by 12 centimeters. Centimeters cancel, we get 2. Again, no units because it's the number of something. Okay? So you can use this formula anytime that you want to figure out what the angle is if you know arc length and radius. So again, let's say we had I'll draw another circle here, and let's say on this one that this is the angle here. We want to find the angle in radians, and we know that the arc length is 30 centimeters, and that the radius is 5 centimeters. Okay, let's just say that that's what we know. So therefore, my angle is going to be 30 centimeters divided by 5 centimeters, and we get, hang on, let me make this 6 centimeters for the radius. Okay, we get centimeters cancel, we get 5. Now, since it's constructed clockwise, I need to put a negative. Okay, so I have to know when to put the negative on how the angle is constructed, to use positives and negatives, just like you do with degree measure. Okay, and that's the definition. That's what a radian measure, the definition of it is. But a lot of you, if you have had some experience with radian measure, you'll know that the symbol pi is used somehow. So let's talk about how pi comes into play and why pi is used so much when we talk about radian measure. So let's look at that real quick. All right, so let's look at one revolution. So we got our circle, we got our angle in here, and let's look at one rev, okay? So we know that one revolution, and we're going to go counterclockwise, is 360 degrees. But now let's also see what it is in radians. And we can do that, let's just say, again here, let's just say the radius here is 10 centimeters. Okay. So how can we use that to get the arc length? Now notice the arc length is going to be this. So in this case, the arc length is equal to the circumference of the circle, because if we go one revolution, the entire outer part of the circle is the arc length. So if I want to figure out this angle, it's arc length divided by radius. And even though I'm not given the arc length, I can figure it out, because in this case, since it's one revolution, the arc length is circumference over the radius. And the circumference of a circle is 2 pi times the radius divided by the radius. So it doesn't matter what your radius is. For one revolution, your answer is always going to be the same. I sub in radius here to get circumference, 10 centimeters. 10 centimeters here. It doesn't matter. It's always going to cancel off, and you're going to be left with 2 pi, which is approximately 6.28 radians. So about 6.28 radii will fit along this arc. Okay? So for one revolution is 360 degrees is 2 pi radians. This is the degree measure. This is the radian measure. So now that's how pi comes into play. Now we can kind of look at converting other angles that we know a little bit more formally into radian measure. So, and we'll just use our standard position, and we'll use our 0, 90, 180, 270. And so right now we know that this angle is 0 degrees, or if we go one revolution, it's 360, and 360 and 2 pi are the same angle. All right. So if we go half of a revolution here is 180. Well, half of 2 pi, so if I'm just looking at this angle, so one time all the way around is 2 pi. Half of a revolution is half of 2 pi, which is just pi. So 180 and pi are the same. So pi is approximately 3.14. That means that if you were to look at this as your radius, 1, 2, 3, a little bit more than 3 radii should fit along that arc. All right? So let's keep going with that. 90 is half of 180. All right? So since this is pi, half of 90 is pi over 2. That should be pi over 2 radians, all right? And then we'll do 270. 270 is same as 390s, okay? 3 times 90 degrees is 270. So 3 pi over 2s is your radian measure. So 3 pi over 2 and 270 are the same. 360 and 2 pi are the same. 90 and pi over 2 are the same. 180 and pi are the same. And then of course I could go clockwise and make, this would be negative 90, negative 180, negative 270, and so on. So one thing we want to be able to do freely is to convert from degrees to radians or radians to degrees. So let me just prove to you a different way that 90 is pi over 2 if I use a conversion. And so here's a little conversion rule, okay? So the conversion rule is this. If I want to convert from degrees to radians, I take my degree measure and I'm going to multiply it by pi over 180. And that just comes from this relationship here. If you notice that 360 is 2 pi, so 180 would be pi if I take half. So that's kind of like my multiplier to help me convert from one measure to the other. So if I take degree measure, multiply by pi over 180, that's going to equal to radian measure. Okay, this is how you convert from degrees to radians. So you take your degree measure, 90 degrees, if you multiply by pi over 180, and then what you're going to have to do is get used to simplifying fractions. 90 goes into 180 twice, your degree units will cancel, you're left with pi over 2. So therefore, I've taken the degree measure, converted it to radians. Let's take one that maybe you're not as familiar with, say 120 degrees. We're going to multiply by pi over 180. We're going to convert 120 into radians. All right, so let's see. So my multiplier is pi over 180. I can see that the 0 degrees cancel right away. I'm left with 12 pi over 18. And what will go into each of those? A 6, right? So we can take a 6. So 2 times 6 pi on the top, 3 times 6 on the bottom. 6's cancel, we get 2 pi over 3. And notice I'm leaving it in exact form because we know with pi, once you round, once you put the 3.14 in, you're rounding pi. Okay? So how do we convert from radians to degrees? Well, it's the same idea here, but now I just flip. I do radian times 180 over pi. That's going to give me my degree measure. So let's just say we had 5 pi over 4, which is a radian measure. We want to convert it to degrees. We're going to multiply by 180 over pi. So let's see. First thing I would do is cancel. So we're let me just write this out to make sure that we're going to convert 5 pi over 4 to degree measure. All right. So I'll take my 5 pi over 4. I'll multiply by 180 over pi. Pi's cancel. 4 will go into 180 degrees 45 times, but I'm not canceling my degree measure because there's no degree symbol down here to cancel. So I'm left with 5 times 45, and 5 times 45 is 225 degrees. You can see an angle of 5 pi over 4, if I wanted to draw that in standard position, 0, 90, 180, 270 is halfway here. There's your 5 pi over 4 angle. So by converting it to degrees makes it also easier to construct that angle. Now, let's just say they don't give you a pi. All right, let's just say that the angle is, let's just say the angle is 6. So theta is 6 radians, convert to degrees. Well, I still use the same multiplier. 6 times 180 over pi. Now, what I'm going to do is, I'll just grab a calculator real quick, type it in and get a decimal. You can round to 2 decimals. So if I type that in, I get 343.77 degrees. And that should make sense because remember, you know that one revolution is is 2 pi radians, and 2 times pi is about 6.28. So if we know our radian measure is 6, think about that. You're almost going to be close to 1 revolution. All right, you're a little bit less than 6.28. So that would be my angle. So 6 radians should make sense that it's almost 360 degrees. So you can see 343.77, we're a little short of 1 revolution. Okay, now to go back to coterminal real quick, did this earlier, got this now. Now to go back to coterminal, let's just say I give you an angle in radians, and we want to know what it is, what are the coterminal angles. So let's just say here's our angle, but now I'm going to say it's pi over 3. I'm sorry, pi over 6. Actually, we'll do pi over 6. Okay. All right. So there it is, pi over 6. But we want to get 2 coterminal angles, one positive, one negative, let's say, but we want to leave it in radian measure. So before with coterminal, what did we do? We said we're going to take our angle and add or subtract multiples of 360 because 360 is a revolution. So the way we're going to do this, if we have radians, it's going to be plus or minus 2 pi. So all I'm going to do is if I want to find a coterminal angle with this, I'll just go 1 revolution from there. So I can, if I want to find coterminal, in radians, I can take pi over 6 and I can add 2 pi. That will add a revolution this way, or I can go and go a revolution back. I can take pi over 6 and subtract 2 pi. And if I do that work there, it should give me one positive and one negative coterminal angle. Now the question is, well, how am I going to add this? Well, this is a fraction. So you treat pi as a constant. We're just going to get a common denominator of 6. So pi over 6 plus 12 pi over 6, and we get 13 pi over 6 is 1 coterminal angle. Here we get pi over 6 minus 12 pi over 6 is negative 11 pi over 6. So all of these angles should land in the same place. And if I convert them to degrees real quick, I can tell you that pi over 6 is 30 degrees. Negative 11 pi over 6 is negative 330. And all I'm doing is I'm multiplying by pi over 180 in my head. Okay? I'm sorry, 180 over pi in my head. And then 13 pi over 6. Well, let's think. What should that be? Well, if this is 30, and we add 360, 13 pi over 6, if you convert it, is 390. So look, add 360, we get 390. Subtract 360, you get negative 330. Okay? So there you go. This is your way. If you want to keep everything in radians, you add or subtract multiples of 2 pi. All right. Let's see. Do you have anything else? I think that's about it. Oh, the last problem, all right? So, let's say that you've got a fan moving. I've seen this, if I've driven up north, I've seen these, do my best here to construct this. All right, supposed to be like a windmill. So this windmill is rotating in this direction, okay? So you've got two types of speeds that we're going to look at. One speed is what's called the angular speed. So it's how fast we're turning this here. And so the angular speed is represented by W. W represents the angular speed. Okay? Of course, R is the radius, or the length from the center to whatever, this is a fan blade. So this would be our R. Picturing this, because this is moving in a circular direction. So R is radius, and V is linear speed. So let's talk about the two types of speeds that there are. So there's a speed at which the fan turns, okay? So you've got the fan turning here at this speed, but notice at this speed, the tip also has a speed too that is moving at. Okay, and it will also be a factor of what that length is. So what we're going to calculate is what's the linear speed, and for this problem, it's going to be the tip of the fan blade. Okay, how fast is it moving? So we're going to need some information. Let's just say that this, the radius is 10 feet. So the fan blade right here is 10 feet long. And let's say that the angular speed is 4 revolutions per second. So 1 second is going 4 revolutions. That's pretty fast for this, but let's just say that's what's happening, okay? So now the first thing I want to do is I want to make sure that my angular speed, my angle is in radians, not in revolutions, okay? So I'm going to make sure that when I work with my angular speed here, that the angular speed is in radians per whatever, per minute, per second. So convert from revolutions to radians. So we're going to say, well, how am I going to do that? Well, we know 1 revolution is 2 pi. Okay? So if it goes 4 revolutions, so we're going to convert this 4 revolutions per second. We know that 1 revolution, you want to convert, but what you want to cancel. 1 revolution is the same as 2 pi. So now you can see what we've done now is we've made it 8 pi radians per second. So you want to make sure that your angular speed is in radians per, not in revolutions. Okay? And now it's just a plug and crank to use this. So V is how fast the tip will be moving. So if we do V equals R times W, the radius is 10 feet. The angular speed is 8 pi radians per second. So we get 80 pi feet per second. Remember, radian is not really a unit. Okay, it's just a number of, and 80 pi, so if I use my calculator, you get a speed there, 80 pi, I get, my velocity is 251.33 feet per second, okay? And that's telling us how fast the tip of the blade is moving. So how fast it's turning here and how fast the tip is moving are 2 different things, okay? And we want to make sure that we can make those calculations. So linear speed is how fast it's moving here at that instant, and then angular speed is how fast it's rotating in the middle, okay? And that's your formula there. I think we pretty much have covered everything, covered these concepts. There should be enough information for you to finish lesson 1, which will make it due into next week, but it will give you plenty of time to do it, okay? All right, thank you.